Welcome and thank you for joining us. If you're joining us for the first time or if you're rejoining us, we're happy to have you. I'm going to reintroduce the webinar series, the new one. It's Integrating Dynamic Modeling and Simulation into Your Courses. Each webinar will be presented by an experienced professor from various fields to highlight how they incorporate dynamic modeling and simulation into their courses. And our aim is to give interested professors a starting point or direction to begin to do the same. Our first webinar is Integrating Dynamic Modeling and Simulation into Civil Engineering Courses by Dr. Rajib Mallick. But before we begin, let's go into some webinar mechanics. So you'll see on the grab tab on the side, and the really important section in this is we are going to have some time for question and answers at the very end. So please add your questions into the questions box. It also has some audio set up. If you have trouble hearing us, you can check there to help that out. Now allow me to introduce today's presenter. Dr. Mallick has taught civil engineering for over 20 years at WPI, IIT in India, and now at the University of Texas at El Paso, and has extensively used dynamic modeling in his courses. He's authored 2 books, including the most recent, System Dynamics for Complex Problems in Pavement Engineering. We are really so happy to have him here today to give our first webinar on this series.
Thank you, Hillary, for the introduction. Good morning, good afternoon, good evening. Thank you for taking your time to join this webinar. I will try to share my experience in integrating dynamic modeling in civil engineering courses and using system dynamics. I would like to acknowledge first my teachers, Professor Mike Radzicki and Professor Khalid Said from Worcester Polytechnic Institute, my colleague and former student, Fred Couts, and of course, Karim and Hillary from ICE Systems for their help, and System Dynamics Society, which has a significant amount of resources for anybody who wants to learn system dynamics. So the content of today's webinar, I would like to just give you a brief overview. I'll spend a little bit of time on why do we model and simulate, just to set the background. What is system dynamics as I understand? Give you some examples of applications of system dynamics in pavement engineering. And why pavement engineering? Because I'm a civil engineer, but I work with roadway pavements as one of the components of infrastructure. So I'll try to explain why I selected that particular topic for introducing system dynamics. I touch on this subject a little bit. How can it benefit students? Because it's important that anything we bring into our curriculum, which is probably already saturated, is beneficial for the students. And finally, round off with some references for you to review if you'd like to. So why we model? Starting from planetary systems to reactions, we try to model because we want to simplify reality as best as we can to improve the understanding of complex systems. And what that does is it clarifies our thinking, and in the process, we create a lab for controlled experimentation thanks to computers on the computer, where we can compress time and space. We can run different scenarios, and we can look at the system structure and wonder, and experiment and kind of test the structures and try to design or redesign them so that we can improve their performance. So with respect to this, system dynamics was developed by J. Wright Forrester at MIT, and it gives us a computer modeling approach that helps us to define a problem by mapping out the important parts of the relevant system and then simulating the dynamics of interaction among the different parts. And you see the sentence that I have in the lower third of the screen. The dynamic behavior of a system is a consequence of its structure. This is probably the most fundamental guiding principle of using system dynamics, that whatever we see is happening within a system is primarily a consequence of the structure. So therefore, we can say that structure causes behavior. And this forces us to adopt an endogenous point of view. We look at the internal components of the system and try to find out the causes of the problems. And in doing so, we understand that to change the problematic behavior of a system, we must alter its structure. Okay. So in a nutshell, what we are doing is we are trying to model a problem with a computer. We are trying to map out the system, and then we are trying to find the root cause of the problem. And then as a consequence, what we are trying to do is redesign the system so that we can eliminate the problem, we can improve the behavior of the system. Okay, so it depends on which software you're using, but primarily I work with Stella. So for Stella, the basic building blocks that we have, and in general, it is the same for any software, but the icons may vary. We have a stock, which is representing an accumulation, which is the collection and discharge, whatever flows into or out of them. And then we have a rate of flow, which looks like a tap, right? To fill a stock, or to drain a stock, or to take away from the stock. Now the arrow indicates the direction of the flow. Then we have converters, which are basic inputs or outputs, and you can have different parameters there. You can run sensitivity analysis by changing the parameters, but those are the places where we keep the parameters. You can have expressions or equations in them also. And then finally, we have the connectors, which show that which one of these elements, the first three elements, are connected to the other ones and how they are connected. Okay. With these, I think it is appropriate to talk a little bit about the mathematics. So what we do when we do a system dynamics modeling, primarily what we are doing is we have a rate, we are integrating it, and we are creating the stock. And you can probably recognize this expression with the second order differential equation. And you can see here that using that and simplifying those expressions, we can create a system dynamics model with two stocks and two flows to represent that second order differential equation. So keep this in mind, because this helps us to understand how the system dynamic model is done, but it also helps us to understand that if we can show with a model, with a real world example, how this is working, perhaps civil engineering students will have a better idea of using differential equations and integrations in their real world applications also. So I think this is a good thing about system dynamics, because pictorially you can represent what's happening with the integration. Okay, let me switch gear now to the applications of civil engineering and try to explain why I chose this topic. As I said, we are going to work on pavement engineering. So pavements, roadway components, for example, are systems that are exposed to the environment 365 days a year, 25 hours a day, and are subjected to traffic and the environment. And obviously, over time, you have deterioration of the pavements, and you can see on the x-axis I have time, and the y-axis I have fatigue cracking. And the cracking happens, the percentage happens, if you look at the data, it's pretty much like an S curve. Okay. And now, one way to put this in front of the students is that you can say it's an S curve and you can give an equation, right? The other method is to actually model it and show how it is changing, and thereby show that the resultant curve is an X curve. I'll show you some examples. But I think that is more powerful than just saying that the deterioration happens in this way. So pavements are dynamic systems because their behavior changes over time, right? There is also the point about the feedback loop or a reinforcing loop, in whatever way you want to call it. We have them everywhere, but with a simple example for the roadway, I'll try to explain. If you have cracks on the surface, and I'm pretty sure you're all familiar with potholes and cracks that happen before you have the potholes, right? They lead to the ingress of water into the system, into the lower system, right, in the base courses, which actually weaken the entire structure. And as a result, you have more cracks, which lets in more water, and you can see what's happening there, right? So the cracking progresses. Now, the initial cracking can happen because of the traffic, right? It can also happen because of, poor mix design or poor structure or poor response or the environment. But once this process starts and there is a threshold beyond which you have this reinforcing loop starting, how do you model this with system dynamics? Why we want to do that? Because it's a complex problem. We do not consider this, so to speak, coupling when we are designing a pavement, right? But we can see that how we can get some good results with system dynamics modeling. And here are some examples, practical examples. So if I look at the total damage of the surface, and if I look at the rate of damage of the surface due to damage of base course, I can get some indications as to where I have the peak damages that are occurring. As well as if I try to seal the cracks, I can get some idea that what kind of sealing percentage would let me have a system that would be resistant to the ingress of water. Okay, so this is solving a complex problem with system dynamics to get some useful answers, right? All right. Dynamics in pavements, as I said, over time, the pavement condition index of the quality changes. So it is something that we want to model over time. There are properties within the pavement system, properties of materials or mixes. For example, in this case, it's the voids that change over time, and we would like to explore how they are changing over time. The properties of the components of the system. For example, this is a mix, and this is a property of the asphalt binder. That also changes over time. So remember, I said that when you have system dynamics modeling, we take a problem, we map out a system, and we look at the behavior of the different components, how they are joined together and how they're interacting, and then we find out the behavior of the system. So that's what we are trying to do. That if I have the moisture of the base, if I have the properties of the binder, for example, and the properties of the mix, can I go back and take a look at the pavement condition of the quality as it is changing over time? Okay, so components to system. All right, let me talk about the first application. And these are practical applications. I think you can relate to these things quite easily from your everyday life experiences. If I have a poor joint in a roadway, what happens is over time, the water gets inside, rainwater, for example, gets inside the pavement through these joints and ultimately damage the lanes that are adjacent to these joints, even though these lanes may be of good quality. Okay, and you can, if you're traveling along a road after rain shower, you have probably seen the water seeping from the joint, right? This is a practical example. This is a practical problem. How do we try to model this, right, with system dynamics? So we can see that the problem is the water ingress through the poor quality joint, which damages the adjacent sections. And then when one lane is damaged, the other lane also starts getting damaged, right? So here you can see a schematic of the problem as we have. Before we jump into the system dynamics modeling, we can see that initial damage in section 1, rate of increase in damage in section 1 at any time after construction, and there is a relationship between those parameters and the equivalent parameters for section 2. Okay, so here we are trying to relate the damages in these two sections, and the damage in one section is affected by the damage in the other section, but once section 2 is damaged, it starts affecting section 1 also. Okay, so how can we model this? We can model this with system dynamics, and what kind of results we can get. So if you look at the left-hand side, you see here that if I consider the sections to be the same initially as far as quality is concerned, and they're disconnected, so there is no connection between them. One section is not affecting the other. The damage in one section is not affecting the damage in the other section. We can get some indication about the damage after construction. And you can see that we have a very good S-shaped curve, and we can be happy that, well, these sections are going to last for 14 years before they are completely damaged. Of course, we are not going to wait until it is completely damaged. We take preventive actions. But if we connect them, what happens? And if they are not at different, if they're not at the same initial condition, then also what happens? So if they're not at different initial conditions or initial qualities, but they're still disconnected, you can see that section 1 and section 2 deteriorate at different rates. What happens if they're the same condition but connected? You can see here that obviously they are getting to a full damage earlier than what we have in this case where they're disconnected. And then the most realistic scenario is that what happens if they are at different qualities and they are connected, which means they are affecting each other. You can see how drastic is the damage and how quickly it happens, 5 years as compared to 14 years. Now, this is not a hypothetical scenario. You can take the data from your field, you can take the data from your research and fine-tune these models. But the main thing is that you can predict the effect or the impact of one section on the other with dynamic modeling. So in general, if you take 6 sections instead of 2 sections, and if you have an elevation difference between those sections, and generally you have elevation sections, right? In some parts of the country, you have flat, no elevation change practically, but in most cases, you do have elevation changes. And if you know that the elevation of section 1 is higher than section 2, and it progressively goes down along this, you can actually figure out how the damage progresses in the different sections and which section actually is the most critical, which will be affected the most. Not only that, you can run sensitivity analysis and you can see the range in life, you can get confidence intervals, and you can see how it changes with the different sections. This is the utility of system dynamics modeling for this application. Let me go to application 2. So I said that there's a traffic, it cracks the surface over time. There is ingress of water, there is damage in base, and as a consequence, the structural capacity is reduced and there is damage in the surface layer. And you have more cracks, more water. Okay, and I refer to this picture before. How do we model this reinforcing loop? Because if we model this, we'll be able to tell how quickly the pavement will fall apart if we have a threshold cracking, as well as how much do I need to seal in order to prevent that. And this is an example of a stellar model. This is an example. This is not very comprehensive, but it tries to take into consideration the most critical things. And what is important here is to see that I have 2 sectors, the surface damage and the base damage. You can run these models individually in the different sectors, and this is a good feature of Stellar that I like. And at the same time, you can also join them and see how one is affecting the other, right? What good does it do? Well, a lot. You can see here that if I look at the damage of the surface without the impact of the base, I have a pretty good 16 years until it reaches 1, right? And the base is, we are thinking it is unaffected, right? But what happens if I consider the effect of the base on the surface and the surface on the base. You can see here that we have clearly the impact on the base, the damage is more, as well as an impact of the base on the surface. And you can figure out what is the rate of damage at the surface due to the damage of the base, where they are peaking, and what is the total damage rate of the surface. This is very important. Let me go to application 3. Many of you have driven during rain showers on the road, and you know how the splash and the spray is dangerous because you cannot see, you can have accidents and things like that. So one of the things that road engineers would like to use is a permeable friction course, which actually lets the water go through them, drain quickly, and avoid the splash and the spray. However, this kind of layer needs a lot of air voids to drain the rainwater as it falls, which also has a consequent problem. What is the problem? If you have high air voids, you may have problems with the stability of the material. The voids can become clogged over time, which reduces the utility of this entire layer, right? So this is a perfect example where you have many components of a mix. And you know, as civil engineers, we have to deal with infrastructure components, mix, constitutive relations, environmental factors, a whole lot of factors, right? But let's try to zoom in on the problem. The problem is we have a mix which is good in terms of draining water, but because there are several components in it, it can actually reduce the utility of the system very quickly. How do we model this problem and find out an optimized system for that mix? So the basic idea is to optimize the different components so that we have a behavior that is desirable. And this is an example. I know Karim is probably thinking that this model is unbelievably cluttered, and I agree. It is not very well placed. But what I want you to focus on is the different parameters that I have in this model, which are relevant parameters. So for example, I have permeability, which is letting the water flow through. I have maintenance. I have polish resistance, which actually is related to frictional resistance. Wet weather friction is a big deal, as you know, how quickly I can stop the car when I push my brakes when it's raining. I have noise absorption, which is also an important benefit of having porous materials or porous mixes. And then finally, what I have is a durability index. And this is trying to give us a composite index that takes into account all the different properties that I have, properties that are coming from the different components, right? If I model this, the results that I get are very instructive. If I don't have any maintenance, what happens to the permeability of the system? You can see it goes down very rapidly. And remember, permeability is the ability of the material to let the water flow through the system. If permeability drops drastically, it's not doing its job, right? Also, if I have durability index, I can see how it is behaving over time for conventional mixtures. Now, if I have a system where I'm using regular maintenance, so you have these vacuum cleaners, so to speak, which actually unclog the voids, I will end up with a system that has a very steady permeability over the years. And this is desirable, which means it is performing well. At the same time, if I use high polymer content in my binder, I can see here that not only I have high permeability, but if you look at the rotting potential, it's quite low as opposed to these cases, right? So now I can design a system which has high permeability, good utility for draining the water, giving us safe pavements, and at the same time, not worry about stability because I'm using high polymer content and I'm getting a very stiff mix. Stiff is a very confusing word. I should say a very high rot resistant mix that gives us a long lasting mix, right? So it helps us to optimize a system to give us desirable performance on the road. All right. Let me come to sustainability. And there's a lot of talk about sustainability. I try to work on my problems and illustrate how we can have sustainable solutions. So I try to first have some idea about the questions and answers that we should be asking when we are building infrastructure components like roadways, right? So the first thing is that we do need roadways because the number of vehicles is increasing, our population is increasing, right? So what happens to roads over time? As much as we try to build them in the best possible way, we know that over time, due to traffic and environment, they will deteriorate and we need to maintain. And if we have to do a major work, we have to rehabilitate them, right? What is the impact of that? Well, anytime we construct a roadway, we maintain or rehabilitate a roadway, we have to spend raw materials, for example, aggregates, which are natural aggregates, energy, labor, and of course, money, right? And if the cost of fuel increases, which always increases, I guess, you have the overall cost increasing as well. How does that affect the environment? So if we talk about, let's say, an area or a city or a county, anything that you want to model, we know that transportation, transportation by trucks, for example, diesel trucks, end up contributing to the release of greenhouse gas, let's say CO2. And we also know that there is absorption by the trees of CO2. But what happens if we cut down the forest and at the same time build the roads, right? What happens then? We are creating more greenhouse gas, and we are also cutting down the mechanism which actually helps us to absorb or remove the CO2 from the environment. Okay. And then finally, how can we say that we can do these things sustainably with the consideration of the road quality, the CO2 generation, dissipation, fuel costs, and everything? The inherent philosophy in this approach is that we do admit that we need roads. Without roads, we cannot survive. But at the same time, we know that when we build the roads, they are resulting in some things that are not desirable. So the question is, how can we make the system sustainable in terms of engineering, quality of roadways, the environment, as well as the economy? And this is where the modeling through sectors comes very handy. So you can have a sector which is the population growth and the road building. You can have one with the sustainability index. You can have an environmental sector. And then finally, you can model this with a composite index. This is a composite index. This is not the composite index. You can come up with several composite indices if you want. But sustainability index, for example, can be denoted by a combination of road quality, fuel cost, and carbon dioxide, right? And then the goal will be to experiment with different things. What different things we are talking about? So for example, if I can recycle roadways, right? Reuse the roadway materials. There are different things, but let's stick to recycling of roadways. Then we will see that how it impacts the sustainability index, how it impacts the natural aggregate stock and everything. So this is the road construction rehabilitation sector. This is the economic sector. This is the environmental sector, and this is the sustainability sector. If you look carefully, you will see here that I have something called fraction indicated aggregate use recycled, right? So I can actually play with this recycling ratio and see what is the impact on the sustainability of the system. And what are the results? So here are a couple of results. First of all, if you look at the sustainability score, which tells us how sustainable the system is, we can see that if there is no recycling, obviously my sustainability score goes down, right? If I have 10%, it goes down less. If I have 40 and 80, they are actually going up, right? So they are remaining at a fairly high level. At the same time, if you look at the natural aggregate stock, you can see that if I don't recycling, it's going down very rapidly. By the way, these numbers are not important. These numbers are assumed numbers. You can use your own numbers for your locality or for the area from where you're getting the natural stock. The key point is the trend in the data over the years. And you can see here how big of a difference we can make by 80% recycling in comparison to no recycling. Okay, and this is the utility of system dynamics. Now, climate change has been talked over, and it's a very pertinent topic these days. How does it affect infrastructure components, particularly pavement life? So if we can predict with some confidence, of course, with some standard deviations and variabilities, what is the change in maximum air temperature for your project location? What is the change in seawater level, if that is relevant? Change in number of category 3 or more than that hurricanes, and change in average annual rainfall over the years. Can I tie them to the properties of the pavements, roadways, and then predict what's the deterioration rate of those pavements? Why it is important? Because then it will tell us how quickly the roadways will fail. And I'm saying how quickly because in most cases, these parameters are worsening. They are going to the bad side, right? In most cases. So if I have these things happening, what is the impact on the deterioration of the pavement? That way I can tell how we can improve the pavements so that they are resistant, or probably the more appropriate word is resilient to the impacts of climate change. So here is an example. If I have the maximum air temperature increasing in a zone, for example, in West Texas, where I live, it's predicted to increase. It creates an increase in the pavement temperature. And as a result, you can see over the years, if we design the pavement in the same way as we are doing right now, we can expect a shortening of the pavement life over the years. Okay. Similarly, if I have precipitation increase, so where I lived previously in the northeast of the US, precipitation is going to increase. It's predicted to increase over the years. And you can see here that if there is an increment, I can clearly see that the average pavement life is going down. So this helps us to understand the implications of climate change on the infrastructure components and have some models with which we can experiment and find out how we can make the infrastructure components more resilient. Which brings us to the concept of resilience. Now, as I said, that we can predict with some variabilities what's the maximum air temperature increase or the rainfall increase and things like that. And I said that we can improve the construction and design and construction of the infrastructure components like roadways to make them resilient to climate change, right? But how do you justify a specific investment? Because no one has, plenty of money or unlimited money to improve the design of the construction, which typically requires investment of more money than what we are using right now, right? So here, what we can do is we can do probabilistic simulations with system dynamics. So couple the system dynamics with Monte Carlo simulations. This is something I think is very important for civil engineering students. In a rare cases, we introduce Monte Carlo simulations, but I think it is very important. So we can take the model that we discussed in the last application, and then we can run them and find out that for the different cases of changes in climatic conditions, what are the rehabilitation cost increments that are projected in the next 15 years. And then what we can do is we can say that if we invest more money with high modulus asphalt, for example, how much investment is justified if we want to make them the same as if we invest the money in a bank. In other words, I'm trying to invest in the road and prevent the expense of more money in the future. And that savings should be the same as any savings that I would have in the bank if I invest some money. Okay, how much is that? So we can do a probabilistic simulation and we can come up with those numbers. Let me go to the last application that I have in this webinar, which is system of systems. So in many cases, you have airports that are on the coast and that get affected by hurricanes, storm surges, for example, extreme events. How do you investigate the resilience of such a system? An airport is a system of systems because it has a lot of components. For example, the runway component, the substation component, the lighting component, the air traffic control tower components, and things like that. How do you look at these different components and find out the resilience of the system or the vulnerability of the system? So we can derive mathematical expressions for asset integrity, and we can couple them. What does that mean? So if I have a single asset independent, I can say that this is the asset integrity where this is the failure level, and we can derive dependent asset integrities by coupling them, and you can go on doing that for several independent components, right? The LCE represents the lowest critical elevation, and the DFL is the depth at which it will fail. So here is a system of systems modeling, which of course can be done in sectors. Here is an example. You can nicely model arrays with arrays, which lets you relate multiple components of one sector to multiple components of another sector. Okay, so arrays is I think a very good feature in Stella, which we can use for multi-component modeling. And this is zooming into one simple component where you can see that if I have the impact of storm surge, I can look at the flood level and I can see the different impacts from sea level rise, maximum storm surge heights. What do we get out of this? You see here I have two graphs. In the left hand side, you can see the vulnerability of the ATC tower is much higher to the maximum storm surge height compared to your airfield lighting board. What does that mean? That means the ATC tower will stop functioning, or the runway will stop functioning much sooner, and that will impact your entire airport. However, if I add a lowest critical elevation, which means I can add a wall to prevent the water from getting inside, I can see that I can reduce the shutdown time from 8 hours to 0 hours, make it insensitive to a 20-feet storm surge. So this is very powerful because it helps us to understand the impact of a natural phenomenon on a system of systems by zooming in the different components. And these are the results you can see for the different integrities. The pink one, for example, is the ATC tower. The red is the runway. These are the airfield lighting vault, and there are various components in a airport system. Finally, with these kind of simulations, you can ask the students to create interfaces, which can be launched in the web, and people can play as a dashboard, like a computer game, to find out what's happening in different scenarios and experiment with different things. And I think what I feel is that student motivation can be improved greatly when they can actually publish their models on the web and let other people play with them. Okay, so as I said, I'm going to round off with the benefits, right? If it is not worth benefiting the students, then it's probably not worth putting it up there. What I feel is that SD system dynamics helps by developing an ability to conduct experiments, analyze and interpret data, to apply engineering design to provide solutions that are sustainable solutions that relate to public health, safety, welfare, and different things that are important for our welfare, and generate enhanced learning about complex systems, because many times we try to understand whether they can apply what they have learned in a system that is complex. What do I mean by complex? So for example, a complex system is one in which the results are unpredictable. Sometimes they are counterintuitive, and you cannot solve the problem with one set of equations or many sets of equations. You have to simulate them, right? And I think you will find many instances in the literature where systems thinking has been appreciated as a primary tool that enables students to think about social, ethical, and moral consequences of what they are designing and constructing. And it can overcome some of the barriers in classroom type teaching. I mentioned that you can say that this is a model, this is an expression, this is a math, but when you actually go through the system dynamic process and you see how the components are interacting, they become very interested and they can clearly see that what is the impact of the components on the system. And finally, this is very recent, I found out that National Academy of Engineering President John Anderson recently said that engineering education should probably put more emphasis on systems thinking in the curriculum based on the different kinds of challenges that we are facing. So suggestions for presenting system dynamics. Very important that the examples and motivations are given with respect to the systems and processes with which the students are familiar. So that's why I have to spend some time to explain roads and pavements to students if they have not taken those courses. So you can provide it as a standalone course. You can do it in small modules, for example, sustainability and resilience with respect to energy consumption, economics, CO2 emissions, water resource, urbanization, and climate change impacts. You can certainly assess how effective it is by pre and post course survey by asking questions like, what do you think caused the pattern depicted in the reference mode, which is as it is the system. Compare the quantified mental models, content, structure, complexity, and dynamics over the time as students get more exposed to these systems, and then estimate the effectiveness of system dynamics. So in summary, system dynamics provides a methodology and tool to solve complex problems. It allows a systems approach as opposed to the reductionist approach. It helps us to analyze, simulate, and predict a system behavior over time, which we may not be able to do with other methods. And it also helps us to determine the key leverage points so that we can alter the system's behavior over the long term. And then when you have done the modeling, I think it overall helps the students to develop critical thinking, conduct experimentation, and very importantly, once you have such a system which is very visual, it helps them to arrive at a consensus and present these results to the audience in a way that they feel comfortable with the results and the approach. So here are some references if you want to look at them. Of course, there's plenty of references on system dynamics, and as I said, I'm grateful to my teachers, and I still consider myself as a student of system dynamics. This is a wonderful topic, and we have many ways of including them in civil engineering. Thank you for your time and for your patience. If I can answer any questions, I'd like to try. Thank you, Hillary.
Thank you, Rajib. There are no questions right now, but we'll definitely take some time to wait so people can have a chance to type some in.
Sounds good.
So one question is, how long did it take you to feel confident to build a model?
It depends on the model, right? The problem. So are you asking the question from the perspective of the teacher or the student?
Well, how about this, you personally?
Well, if it's a complex problem, obviously it takes a very complex problem. We try to model complex problem. It's a very complex problem. It takes time. But I guess the key answer is that we look at the problem and we try to model the problem. And invariably, in the first pass, we have many things in the model, and then we try to simplify the model and just keep the bare essentials so that we can have a nice, neat model. So I would say that for the type of problems that we encounter, that we try to solve, it probably is an exercise that can take a few weeks, But obviously, when you are giving the models to the students to develop in their classrooms, you like to start off with very small elementary models and then build up and go more and more complicated models. So if I give the models to the students, I'm giving models that they can develop probably within a week initially, and then probably a couple of weeks in the latter part of their course.
Great, thank you. Another question came in is, how do you, could this be applied to sustainable buildings?
Of course, yes. As I said, it's a very good question. Yes, of course. It can be applied to any infrastructure component that we envision. I think the potential is limitless. You can apply to buildings, you can apply to roads, you can apply to airports or ports. And it's very important, as I mentioned, that when you are presenting this to the students, make sure that the students are familiar. For example, if it is sustainable buildings, they are familiar with the theories and the design and the construction of buildings and sustainability, so that they can relate to those things when they are modeling. It should not be like they are modeling something with which you're not familiar. So the subject knowledge is important in order to have that. But the answer is yes, you can do it for sustainable buildings.
Another one is, can we say that roadways are built differently considering climate and usage? And in your experience, how many city planners or transportation decision makers integrate systems thinking into their decision-making process?
Well, we can say that roadways are built in different ways because they have to sustain traffic and environment. That's a big part of our design process for roadways. And the second part of second question, whether how many, I think many city planners consider system thinking, but you can integrate systems thinking in different ways. System dynamics, I think, is the most elegant way of integrating systems thinking. I'm quite, I have not surveyed, but I'm quite sure that many of them are using systems thinking, and most of them probably are aware of that, or are using system dynamics modeling in some sense to look at infrastructure planning and modeling. But I think there is scope of more use. Definitely, there is scope of more use.
Another one is, what about the problem becoming more complex, such as defined by PDEs instead of ODEs?
Yeah, so I see what you're saying. You can model as much complex systems as you want, given that you have enough resources of time and energy and access to the software. The key thing here is that when we try to model something with system dynamics, we not necessarily want to predict some numerical numbers or actual results. What we try to predict more is the trend and the behavior of the system. The individual numbers, as I mentioned, is not that important, are not that important. What is important is the behavior of the system. So what I would say is that when you have a very complex system, the approach should be try to simplify it as best as you can, not more than that, and then try to model that. But yes, you can do as much complex modeling as you want. There is no end to this system. All you will end up having is a large number of stocks and flows. And just like the mental modeling system, at some point it will go, I think, beyond our capacity to manage that. But the answer is yes, you can do that.
And sort of a follow-on question to that, is for such complex models, how do you tell the completeness of the model in representing the system?
Well, good question. For the rule of thumb is that you output or you run the model, you simulate the problem, or you simulate the system, you find out the results, and you compare the results with your reference mode. The reference mode being the data that you have from experiments or historical data or any kind of data that you have from reality. So we know that the system is functioning, the model is good, and good is a very dubious term here, but the model is useful. Let me say the model is useful when we see that the behavior of the results match with the behavior of the reference mode. And there are other things as well. For example, you look at providing like a shock to the system. So if you change the key variables drastically, is the system sensitive? Or the results showing that they are changing? Also, by intuition, you know that if I do this and do that, the system should behave this way in the short term at least, or it makes sense. A few things, not all of those things. So you can check those, right? So there are established rules of making sure that the models are useful and the models are fairly accurate or in the right direction. So yes, there are sets of rules that you can follow.
When it comes to teaching, how have you been offering SD courses in your civil engineering program?
Yeah, so initially for a few years, I inserted system dynamics as a module in a resilience course where we looked at the impact of extreme weather events or climate change on infrastructure components. And then we tried to model in one module and then show the results, what are the impacts, and then let the students design the system so that the components, infrastructure components, are more resilient to the impacts. But lately what I have done is I have introduced a graduate and undergraduate level, upper undergraduate level course where we have system dynamics modeling, systems thinking as the main thing with examples from roadway infrastructure and components. So the idea is to give them the opportunity to work with a set of models, or should I say, set of problems throughout the course. Let them model those problems and develop their knowledge regarding how to model, what are the best practices, adopt those best practices, get some insight, and progressively develop more critical insights and more complex problems, more complex models, so that they can solve bigger problems.
And how are the relationships and influences you've uncovered the same considering the climate changes, i.e. the only changes are the values of the converters?
The only changes that are the values of the converters. Yes, as I said, you can do sensitivity analysis, you can do probabilistic analysis. So what I have done, and I'm sure you can do it in different ways also that I don't know of, you can use the converters to put those expressions or numbers, and then you can run sensitivity analysis with those numbers and see the results. But at this time, I have used the converters to indicate the changes. Yes.
How do you estimate the indices for different variables?
Indices for different variables. So what I'm guessing is the question is, how do you figure out the expressions or the numbers that you? So those are actually based on research and analysis. So for example, if I have conducted an mechanistic design of a roadway based on certain material properties which are affected by temperature, I should know that if the temperature changes by X, what's the difference, what's the impact on the modulus or the stiffness of the material, and hence what's the impact on the age, not the age, the deterioration model of the pavement, okay, or the life of the pavement. So if I have that, and if I run this with different climate change scenarios or different numbers, I can develop expressions that relate the climate change to the life of the pavement. And so this gives me one example of a model that I can use as an expression in the system dynamics model to predict what's happening as a result of climate change.
And there's some people that are asking if you are available for follow-up questions later after this webinar.
Yes, I think, I don't know, you have my email. I'll be glad to try to answer questions if they can send me the questions by email.
Okay, we do have your email, so if you're comfortable with that, we can contact those people.
Yeah,
okay,
sure.
Okay, there's one last big question. Can considering highlighting SD capability to support the creative phase and pushing the increasing holistic thinking? For example, environment is composed not only of vegetation, but also wildlife. Roadways can interfere with wildlife migration behavior. Should considering strategic placement of overpasses, which conserve natural wildlife well-being, as part of the scope of the road construction budgeting?
Yeah, this is a very important and good question. The short answer is yes, it should be. Wherever it is relevant, it should be considered, because the whole purpose of doing system dynamics modeling is to have an empathetic view. We should be considerate of all the aspects that are affected by road construction and design, not only the engineering aspect, but the wildlife, the vegetation and everything. So this is a nice topic that can be easily modeled with, well, I take back the word easily. It can be done. It can be done with system dynamics, and it will be a fruitful process. It will be a very useful process to model that. And I support holistic, views of design and construction of roadways, and you can include that in system dynamics modeling. I wish people do more of system dynamics modeling when they are planning for roadways, rather than when they're designing and construction of roadways. As I said, it's very important to look at the system and behavior, not numerical values. So I would rather see the impact on wildlife and vegetation when you're planning for roadways than to actually try to figure out what should be a content of a specific material from system dynamics. System dynamics is not, or should I say, system dynamics is more important for the former than for the latter topic.
Okay, we have one more question, and that's all we have time for. So the last question is, the relationship between variables from literature that you may have borrowed are usually not causal relationships. How do you address this to refine the relationships in your models?
Right, that's an important question. Yes, there will not be causal relationships. There may be causal relationships, right? So, for example, if I'm looking at a component, two components which are affecting the behavior of the mixing of those, the behavior of the mix of those two components, they are definitely causal. But you have to be careful. You have to make sure that the relationships make sense. And within the span of the modeling period, you need to figure out that they are making sense. And as I said, check whether they're matching, the results are matching with your reference mode. If they're not matching with your reference mode, then there must be something wrong, right? Reference mode, again, refers to historical data or actual data. So that's a good question. And the answer is you have to make sure that they are causal relationships, at least, for the part of the model that you are designing.
Excellent. Thank you so much for your presentation. This has been recorded, so we will be posting this in a couple of days so people can review this again. But thank you very much, and we hope to see you all in other presentations through this series.
Thank you, Hillary. Bye.